Welcome back, ladies and gentlemen. We're going to be taking a look at another graph, another position time graph, and we're going to convert it into a velocity time graph. But unlike the last graph we did, this one has a curved section, two in point of fact. And that's probably going to throw us a little bit because we haven't done a lot of those, right? In grade 10, we mostly did flat sections or slope sections, but now suddenly there are curves. So how do we deal with this? What do we do? And more importantly, do we have to do all of the work or can we be clever? I hope we can be clever. So, first things first, as is always the case, let's take a look at our graph and see if we can figure out how to cut up the graph. Now remember, we're going to cut it up every time there's a change of shape or change of sign. Those are our two criteria. So, let's get our trusty red and let's see what we got. Our first section here is curving. Okay, so this is clearly our first area. Down here, we've got a flat part. It's a very small flat part, but it's a flat part nonetheless. This is our 2. Up here, we've got another curve. It's curving away from that flat back towards the axis. That's a 3. Here's a slope. That's going to be our 4. Here's a flat. There's our 5. And here's another slope. That's our 6. So we have a total of 6 different segments that we're working with. Now, before we start doing a bunch of math, it's important for us to remember to check what the shapes look like, because if we know the shapes, it gives us a guiding principle, a guiding lamppost, or what am I looking at here? A lighthouse in the distance that we can use to make sure we don't get lost. So remember our pattern. We've seen it before. A curved line becomes a sloped line, becomes a flat line, becomes a zero line. This pattern is going to see us through here. In this particular case, let's draw ourselves a real quick sketch. Okay, this one here was our position graph. Now we're going to do a velocity one. Now we're not doing any numbers, but we're going to be able to draw the shapes because we can use our pattern and our brains. Okay, we'll do the easy ones first. 2 and 5. Those are both flat lines, so they become 0, right? Because on a position graph, flat line means not moving. So on a velocity graph, they're not moving. But I have to mark them as not moving. Not moving on a velocity graph, how do we show that? We put it at 0. There we go. So 5 is easy. 5 stretches across this whole section here, just like this, across the axis. Now, 2 is a little bit trickier, but thankfully I've drawn my graph directly over top of itself, so 2 is a little dot right there. Now, I know those aren't easy to see, but there they are. We've got a dot here directly underneath 2, because it's on the axis, because it's 0, right? Flat to 0. And now this corresponds to this section. So we've got 2 things done. Great. Well, that's only a third. So we've still got a little bit more to go. Let's take another look at it. Section 6. Section 6 and 4 are both sloped lines. So a sloped line here becomes a flat line in the next graph because we have constant velocity. There's no acceleration here. Okay, so this is a negative slope. So that means somewhere over here we're going to have a negative flat line. And they're going to be connected vertically, like with some dotted lines. Now, this one here, from about 9 to 11 seconds, that's a positive slope. So that means that from 9 to 11, which is about from here to here, we're going to have a positive flat line. Okay, this is looking pretty good. We're now 2/3 of the way done. We've only got the 2 curved sections left to do, section 1 and section 3. Now, curved sections, that means tangent lines. That means all sorts of complicated calculations that we might not be familiar with. Oh wait, we're not doing calculations yet. We're just following the pattern of the shapes. So let's take a good look at those shapes. This is a curved line. A curved line becomes a sloped line on the next graph. Okay. So now the question is, what type of slope do we want? This curved line right here is starting off very sharp, and then it is flattening out when it gets towards number 2. So we started with a number, and we're going towards 0. Okay, well here's the 0, but we had to start with a number, and this is a negative slope. This is probably the single most complicated one to do. But what that means is that we're starting down here, and we are extending with one line to 0. a single sloped line that started off with some kind of value, because this started off quite sharp, and then it flattened. So it started off with a value and it went to 0. That one's the most complicated. Let's take a look at the next one. We've got here a curve that starts at 0 and is going to get faster. It starts off flat and it becomes sharper over here, right? If I cover this part, that just looks like a sloped line. If I cover this part here, oh, if I can get my hand right, that looks like a flat line. So what we're trying to do is to see if we can understand what's happening with those shapes. Or the clever people will notice here, like, come on, I got to go from here to there, and I got to use a single slope line to do it? Well, that has to be something kind of like this. Okay, so we have now drawn a rough sketch of the graph without having done any calculations. That's great. Now if we can just put some numbers to this, we're basically finished. The question is, how many numbers do we need to calculate? Well, some we have to calculate more than others. Section 2 and 5 here, they're basically already done, aren't they? Because they're just 0. So 2 and 5 are finished. Little check marks. Now, these two are flat lines. We know how to calculate those. Those are really easy to do. So let's do them, right? Those will be super simple. So let's take a look at section 4 and section 6. Now, both of those are using a slope of a line. So they're both using slope is equal to delta y over delta x. But they have different numbers. Now, I have conveniently marked a bunch of the numbers on the graph. Obviously, your particular graph, you have the whole grid, so it's easier for you to read. But let's take a look what we got here. For number 4, we're going to be doing plus 10 as the final one. That's the one that's way up here. Minus, well, 0, because that's where we are at 9 seconds right up here. Similar, 9 seconds minus 11. All right, so if we solve that, we're going to get that this is plus 5 meters per second. Okay, cool. So now we have an upper limit on our graph. That means I can come over here and say, hey, this flat section over here is at plus 5. Sweet. Okay, what about 6? Now, 6 is a little bit hard to read. It's 6.25 or so on your graph. So if we put those numbers in here, let's do that. So we've got here 16.25 and 20 all over 10 and minus 3. Okay, so we set that up, and then we do our calculation, and when we work all that out, we're going to find ourselves with negative 3.5 meters per second. All right, well, that's great. So that tells us now that number 6 down here is going to be negative 3.5, give or take. Well, sweet. If we have 4 and 6 solved, that means now we have got 2, 5, and 4, and 6. We have now got most of the graph squared away, and we've only had to do 2 calculations, 2 very simple, 2 very familiar calculations. Of course, that's not why you clicked on the video. You probably wanted to take a look and see, how do I do the part with the slopes, with the curves? How do I do the tangent lines? Well, here's the important part. Only do the tangent lines if you have to. So we have to do 1 and 3, right? Both of those still have to be solved. But take a good look at 3. 3 is a line, a sloped line, right? Curve to slope. It's a sloped line that has to go from 0 to plus 5. It has to go from here to here. There is only one line I can draw that goes from here to here. This one, the one that I already drew. I don't need to solve anything here. I don't need to find out what the number is because I already can draw it. It's already finished. So the fact that it's a curved line up here on this other graph, number 3, doesn't matter. I'm already done because I knew the boundaries on either side of that section, right? This curved line here, number 3, was bounded by a slope line, easy to do, and a 0. aka a flat and a 0. So because of that, this is automatically done. I just connect it because I can see the pattern. Now, you might be thinking, okay, Mr. C, cool. We've got a trick. We managed to avoid having to do any calculations for 3, but what about 1? Can we do the same trick for 1? I mean, you did draw this like this. Are we done? Unfortunately not. So here, I know this was 5 and I know this is 0. Or at least now I know they're 5 and 0. But I don't know what this dot is down here, right? Is this 10, 20, negative 10, negative 20, negative 30, negative 2? I don't know. I have to figure it out. But I don't really want to because that would be a lot of work. But I can solve a tangent line. Now, a tangent line, remember, is used to find the instantaneous velocity. It is used to find the velocity of a curve at specifically one spot. So what ends up happening is that up on my curved graph, I can't solve the whole curve, but I can solve a spot on that curve. And I choose one, any one. In my particular calculation that I chose to do on the graph paper, which I can't necessarily show you up here too easily, I chose the time at 2 seconds. Once I've chosen that spot, I then take my ruler and I place it to extend the line that already exists at that point. Now, when I say extend the line, the important part is I got to make sure that I match my ruler with the line that already is there. So how do I do that? Like, how many ways can I put my line? I could do it like this. I could do it like this. I could do it like this, right? Like, there are so many options. What do I do? Reminder, you make sure that the line is positioned in the same basic slope. A good way to tell if you've done that is if the space on either side of the line, either side of the X, is about the same. So I set this up like so. And then I draw a line as long as I want. And there is my tangent line. What I meant by the same size is that this side of the line from here to the curve is about the same as the spacing from here to the curve on the other side. Now, it's a little hard to see here just because of how small the spacing is, but on your page, hopefully you can see that. So always make sure to align the ruler so that way the spacing is about the same on both sides. Okay, once I've done that, I choose 2 points on my new tangent line, and I pull those numbers and I use them in my slope equation. Now, again, I can't really do that here because there's no graph paper for me to work with, but there was graph paper when I was originally doing this, so I'm going to pull my numbers from off camera. So we're doing section 1. We're still looking at the slope calculation. And the numbers that I ended up getting were going to be negative 9.5, corresponding to 3 seconds. And then at 0 seconds, it was minus 2. And this ended up becoming negative 2.5 meters per second. Now again, I can't show you exactly how I pulled it, but it's the same basic idea. You're just going to have to trust me on it. Now, that's what we've got. It's negative 2.5, but what does that tell me? Well, unlike with, say, this one and this one, it doesn't tell me the entire stretch of the line. It's not telling me that this entire curve of part 1 is exactly 2.5. What it's telling me is that at exactly 2 seconds, right here, it is 2.5, which means if I were to bring this down to my graph, at about this place here, I would be located at negative 2.5. Well, what does that do for me? I mean, that's only one spot. X is 2.5. Now I have a second boundary. Remember, the trick I did in part 3 here, section 3, was that I knew 0 and I knew this was 5, so I could draw the line that connected it. And I said I didn't want to have to calculate this one at the bottom because that'd be a lot of work. And I have an upper boundary of 0. Now I've got a middle boundary, which you're like, well, that's not the same thing. Well, actually, it kind of is, because I have to draw one line. Remember, curve becomes sloped. I have to draw one line, and that one line has to go from this point through this point and somewhere onto the axis. There's only one way for me to draw that. I have to do it like this. It's the only way for me to go through those 2 points. which means even though I don't actually know where this is, I don't need to figure it out because I know what line to draw. Okay, so with that, we have now got the entire graph squared away. And notice, in order to do this, we only needed to do 3 calculations. We had to do 2 flat slope calculations, just like we have done before, right, for this part and this part. And we had to do 1 tangent line, only 1, in order to find a lower boundary right here. This section here, we didn't need to do because that section was already bounded on both sides by a sloped line and a flat line here at the 2. So, what's the big takeaway? If we think critically and we use the patterns that we have learned, we can do complicated problems far, far easier. We could have calculated every single one of the 6 parts of this graph, but instead we only did half the work and we got the whole thing. And I think that's a good place to leave it off. So I'll see you next time.